Okay, guys, so we've looked at polar coordinates. We've classified some different types of curves. Now, let's get our hands on the actual calculus involved. So let's start just by developing this notion of area, right? That's one of those big topics in calculus. Excuse me, in calculus. And if you think back to, say, Calculus 1, in your Calc 1 class, when you went to find the area under a curve, you'd have some curve. You know what? I don't like how I'm writing right now. Let me be a little more precise here. So you would have some curve, and you'd want to integrate or find the area between A and B. And we did that by partitioning that interval and then finding areas of rectangles, right? So essentially, in Calc 1, the area under the curve is a sum, albeit an infinite sum, of areas of rectangles. Whoops, rectangles. Okay, well, in other words, we had that basic unit, right? We had some, sample point and some we evaluated the function at, and then some width. So this was essentially height, and that was base. So base times height, you have an area of a rectangle, take infinitely many of them, you get this definite integral. Well, now, in Calc 2, at least in polar coordinates, we're finding the area of what's called a polar region. So you might have some curve, but now this curve is traced out by try that again. Right, by some radius. And so you might have, your first theta be alpha, and you're integrating all the way to maybe beta. And you want the area of this, what's called polar region. Well, you're still going to create a partition, but what you're going to partition now is this angle. And so you might have one of those. Very hard to do with this stylus, but I think you're getting the idea. Okay. And so on. And so what happens is you get these little sectors, right? If I zoom in on one of these, maybe I zoom in, right? I'm going to have some sector here. This might be RK minus 1. This might be RK. And what we can use is some sample point to find the area of a sector. Maybe here. Some R of theta K star, right? Somewhere in that interval. Well, the area of a sector is 1/2 R squared theta. Well, we're going to have a whole bunch of sectors here, right? So the area of maybe the kth sector is going to be 1/2, and then r of whatever that sample theta was taken to be on that interval, squared, and then delta theta, okay? And so obviously if I take infinitely many of these, then I get an expression for the area of the polar region. And so what I get here is, right, if I want the actual area, then I'm going to sum these 1 to n, and then let n go to infinity, okay? But this is simply, by definition, an integral, right? So you get 1/2 r squared d theta, okay? And then keep in mind that this r is really a function of theta, okay? So let's see how this plays out. Here we got a cardioid, okay? And I want to find the area of the region enclosed by the cardioid. Now, notice there are no limits because we need to know what those are, right? So the cardioid is going to start, right, at theta equals 0. And then as this traces out, it's going to come all the way back to where it started after 2 pi, okay? So the area is going to be the integral from 0 to 2 pi of, and then 1/2 r squared, and remember r is this guy, d theta, okay? And so if we clean this up a little bit, we're going to get, well, let's see, we're going to have a 1/2 times a 4, which is 2, so I'll bring that on out. And then 1 plus cosine theta squared, right? Which is just 1 plus 2 cosine theta plus cosine squared theta, d theta. All right, and so then we're going to, and I would encourage you honestly at this point to pause it and just try to see if you can come up with, you know, the right identity to use to break down this cosine squared. But I think you'll recall and then cosine squared, right, is 1 plus cosine 2 theta all over 2. Okay. Which equals, again, I'll let you verify this. When it's all said and done, you should get 6 pi, okay? All right. All right, guys, so let's check out the next one. All right, so we want to find the area of the region enclosed by the smaller loop of the limacon, r equals 2 cosine theta plus 1. And what that is that's all this in here, right? And we can use some symmetry, right? We might notice that, you know, instead of you know, integrating this whole thing, we could just maybe double part of it, okay? And so then the issue is, what is this theta right here? And what is that theta right there? Well, let's think about it. This first theta happens when r is equal to 0, right? And so if r is equal to 0, we'll have 2 cosine theta plus 1 equals 0. So cosine theta would be -1/2. And so that's going to be at 2 pi thirds, or 4 pi thirds. So that first one is going to be 2 pi thirds. And the way this is traced out, right, this is at theta equals 0. It's going to come in like this, and then come down here before it makes its way back up and around. So this, as it comes from above back to this point, we're back at theta equals 4 pi thirds. Well, that makes this point right in between 2 pi thirds and 4 pi thirds, which is what value? Well, pi, right? And so I'm going to double this area down here, okay? Now, please, again, don't think of that as somehow being negative because it's below this x-axis, right? You can't think of things this way. We're in polar coordinates. And so really, that's just the way the trace works, right? Comes down here and then comes down, up, and around. So my area is going to be 2 times that area from 2 pi thirds up to pi of 1/2, and then my function is 2 cosine theta plus 1. Quantity squared d theta. All right? And so now let's just kind of go to work on this and see what happens. Okay, 2 pi thirds to pi, and then 1, well, let's do this again, right? We have a 1/2 times, and then what are we going to get here? 4 cosine squared theta plus 4 cosine theta plus 1, sorry, can't write, d theta, which will be, well, let's get rid of it, right? 2 times 1/2, bring that 1/2 out. So we just have this. So 2 pi thirds to pi, and then 4. But that, again, that cosine squared theta, I'm going to write as 1 plus cosine 2 theta all over 2. Okay. And what will we get? Well, again, this is where I want you to pause it and finish it out. So go ahead and give it a pause and see what you get. All right, so hopefully you went through, did some algebra, and wound up with pi minus 3 root 3 all over 2. All right, here's another one. I want to find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine theta. And so, in other words, all of this region out here, right? Well, when you found bounded areas of bounded regions back in a typical Calc 1, you probably would have needed to find where they intersect, right? Well, we're going to do the same thing. So why don't I have you, again, pause the video and see if you can find where these intersect. Really, give it a pause. I'll be back. Okay, so hopefully you got negative pi halves or pi halves. Now, if you didn't get this negative pi halves, you might be thinking, well, gosh, why didn't you choose 3 pi halves? Well, let's think about this. 3 pi halves would take us from, if you're on the circle, from here all the way down to there, right? And on the cardioid, it would take us from here all the way down to here. Those aren't the regions we want, right? I'm not looking for this region out here. I'm looking for this region over here. So, you know, the direction is important. I need to start at that point. Yeah, it might also correspond to an angle of 3 pi halves, but I need to move this direction. And so I'm going to call it negative pi halves. All right. That lets me set up my integral, right? From negative pi halves to pi halves. Okay. Now we want to be careful because I've got 2 different functions of theta, right? And so I need to have my outer minus my inner. Well, which function has larger radii on this interval? Well, yes, the circle, right? And so I'm going to have 1/2 integral negative pi halves to pi halves, and then 1 squared minus 1 minus cosine theta quantity squared d theta, okay? And so, per usual, if we were in person, I'd have you be doing this too. Again, put this on pause and work out that integral. All right, so after the usual tricks and identities, mark our way down here, and we should wind up finally with 2 minus pi fourths. Should be getting used to, you know, making those double angle identity transitions for cosine squared. So, all right. So the other issue is length of a curve, right? That's something that we've seen, arc length from just functions defined in terms of x, parameterizations, and now here in polar form. So let's take a few moments and develop what we mean and how we arrive at the length of a curve or arc length in polar form. Well, remember that we're really seeing r as being some function of theta, right? And we're going to let theta run from some alpha to beta, okay? Again, we're finding, right, the length of some arc. So maybe that's alpha, and maybe that's beta. And we want to know what this length is, okay? Well, really, we could think of a parameterization, right? We know arc length when we have a parameterization, right? We know that arc length is the square root of dx d theta squared plus dy d theta squared, right? D theta. So here I'm treating theta as a parameter, okay? Right, much like we considered time or t. But let's think about this for a second. We know how to transition here. We know that x is really our cosine theta, which I might as well call f of theta cosine theta. And I know that y is r sine theta, which I could consider f of theta sine theta. Just reminding you that r itself is a function of theta. Well, what is this equation going to become then? Right, dx d theta would be f prime of theta cosine theta minus f of theta sine theta. And then dy d theta, right? We can evaluate that as well. We know that dy d theta would be f prime of theta sine theta plus f of theta cosine theta. And so if you just kind of play around with this, dx d theta squared plus dy d theta squared, this actually becomes r squared plus dr d theta squared, okay? And again, you can square these out and cancel things and you'll see it. And so that gives us a nice formula for the length of a curve, okay? So let's go ahead and find the length of this cardioid, 1 plus sine theta. So I'm going to pause this and go grab the graph for it real quick. Okay, so here we have the graph of r equals 1 plus sine theta. And let's get our hands on our limits of integration. All right, so theta equals 0. Where's that going to be? Well, theta equals 0. That's r equals 1, right? So right there. And we're going to need to go around 2 pi. So there's theta equals 0. Theta equals 2 pi. So we're going to go from 0 to 2 pi, okay? And then we've got this nice expression. R squared plus dr d theta squared, d theta. Okay, oops, too far. So let's see, dr d theta. Well, we can do this all at once here. So 0 to 2 pi square root, and then r squared, that's 1 plus sine theta squared, and then plus dr d theta. So if I integrate r with respect to theta, right? Oh, I'm sorry, if I differentiate r with respect to theta, then we get 0 plus, and the derivative sign is cosine. So cosine theta squared d theta. And now we just do some algebra and see where this takes us, okay? And so 1 plus 2 sine theta plus sine squared theta, and then plus cosine squared theta d theta. And then, of course, we notice that sine squared plus cosine squared is just 1. So we have 0 to 2 pi square root of 2 plus 2 sine theta d theta, okay? And then at this step, as always, go ahead and give it a pause and see if you can take this thing home. All right, and so you should do some work here. And this is not an easy integral to compute. And to be honest with you, I'm not going to require you to know all the half-angle formulas for exams and things like that, but just know that with some half angle applications, so you eventually work out to 8, okay? Again, this is really the big point, right? Getting it to there, and then you have some other tools at your disposal. Okay, the last problem here I want you guys to think about, and I'm going to actually start our time together on Tuesday with this problem. I want you to come in having done some, thought about what this is, because you know, this is a rose, and you might think about how many petals it has. And so, you know, if each petal has a certain area, and if there's any symmetries involved in even a single petal, how does all that play together to come out with some nice way to find the actual area? I'm sorry, not the actual area, but how far that particle actually travels as it moves along that path. So give some thought to this, try it. Please don't Wolfram Alpha it or Chegg it or anything like that. Just see what you can come up with. Go on to Desmos, give yourself a nice graph, and then play around with it, okay? And we'll go over it when we meet on Tuesday. Have a good weekend, everybody.